Hello and welcome to our latest webinar in the series. So it's a year in review, looking back at 2025. Doesn't feel a year since we did this previously. It's gone very quickly, but lots of case studies and information throughout the year we want to share with you today. So firstly, thank you very much for joining. Today, joined by Gareth Devine, myself. I now head up the engineering development efforts at EA Technology, so covering particularly our PD products for today's context. And Stuart Aird, my colleague.
I'm Stuart Aird. I run our PD technical services team. So my team, I'll go out doing partial discharge surveys and cable testing around the world, basically.
Okay. So for today's presentation, we very much want to get into the case studies and show you some information that hopefully will help you make better decisions on site and give you a feel for what we found over the year working with yourselves. We're going to start with a very brief introduction to EA, just to make sure you're on the right call, give you a bit of account of what we do, and also touch on a couple of the main themes from the year, from technology improvements in our handheld area, and what we've seen in the wider market. So probably 5-10 minutes on that, and then we'll get into the interesting elements of the case studies. Okay, so let's get started. So EA Technology. For those of you who don't know, EA have been around now just come to 60 years. So an established company, originally targeted or set up for the Electricity Research Council, looking for uses of electricity in day one. From there, we went on to solve the hard problems for UK DNOs, very much an innovation company, and we've privatised, moved to more of a product and SaaS sort of based company in the last few years. We basically concentrate on helping DSOs, DNOs and industrial customers keep the lights on and make it the right decisions to manage their networks safely and efficiently. We are a global company, so we've got 5 global offices and expanding, and you'll find our products in pretty much every corner of the globe. So that's our PD products or the wider LV devices. What do we do? So EA's got quite a broad church, but it can be summarised really in 3 areas. So reliability, resilience, so making sure the lights stay on. So in the LV network, that's a lot around visibility, around predicting faults and cables, etc., ahead of time and enabling proactive action to be taken. In the MV area, which we're talking about today, it's the UltraTev brand, and we are looking a lot more around partial discharge, the quality of the insulation of the assets. Linked to that, we then feed that data into our asset investment optimization world, which is very much helping guide our customers where they should invest next, whether that be for load or condition, helping them look to the next price control 3, 5, 10 years out, and really managing that wider asset base. The final area is our grid access. This is supporting the decarbonisation agenda, helping people connect new technologies to the network. So if you go on to, in the UK, some of the DNOs and look at their connections processes, you'll now know for LV and MV connections, you can get connection requests approved or fully quoted and approved in order of minutes. It used to be much longer effort, and in some parts of the world, that's multiple days to achieve. That's now done fully automated using our tools. So really every area of the modern network we touch and support in one way, but concentrated around these 3 core bubbles. So that's a little bit who we are. Just for background, this is the latest in a series of webinars. If you haven't looked and you enjoyed today's, please go back and have a quick look on YouTube at these. The links are there. They will give you background to our devices, further case studies, and some tips and tricks of what we're finding useful in the field. So there's some previous ones there. There's actually a lot more on the YouTube channel, and you may find that of interest. So that's enough of an introduction. Let's move on to something a bit more interesting, the technical updates. Okay, so 2025 has seen quite a lot of change really in the PD world. We've hinted on this of where the direction was going in the previous presentation, and this direction away from PD being just a safety device towards monitoring and predicting failure on a sort of wider asset basis and be able to trend that data. So what have we done towards that this year? Well, the first step is we've expanded the capability of the handheld device. By capability, I mean applicability, which switchgear, etc. this can be used with. So starting with the plus in the right-hand corner, as you all know, it's got two inbuilt sensors. So we have a TEV sensor inbuilt and an ultrasonic sensor inbuilt. They were primarily targeted at metal-clad switchgear. We've then added into the UHF range. So there's a UHF expander module, the receiver, which goes into the side of the device. And that increases the input frequency to around about gigahertz and allows us to look in the UHF spectrum, so ultra-high frequency spectrum, at a wider asset base. So in particular, the UHF directional antenna is used now in outdoor compounds, so maybe 132, 400 kV gear, and looking for internal issues with inside insulators. This has the advantage that it ignores corona and very much looks at the damaging PD, the stuff you're interested in. So unlike some of the cameras on the market, it focuses you down to the bits that's really key for your asset management. Linked to that, we've added a GIS band antenna. So this allows us to look at more the tubular GIS on the spaces for supporting spaces. Again, typically 132 kV and above, and allows us to do spot measurements on the large GIS installs. From an OEM point of view, or from a retrofit internal install, we've brought out internal antennas, and you'll find them installed right across the market now, typically in cable boxes, and they'll provide coverage of that whole compartment, again linking out to the handheld device. So big expansion in the UHF area and taking it away from metal-clad switchgear to outdoor compounds and higher voltage assets. In the coupling devices, so looking more at the TEV type coupling and other options, we have the locator, which has been an established product for a while now. So that helps us narrow down where PD is coming from the TEV area. But we've also brought out the VPIS sensor. So that's probably been out for a couple of years now, but we've really seen a big adoption this year. And that's allowing us to very quickly look panel by panel into the VPIS sockets on the front of the switchgear, and allows you to narrow down PD to the phase and very simple, quick, repeatable measurement. So it's literally as simple as the two formal connections, hit record, move on. So that seems some wide adoption because of that. Finally, the well-established HFCT approach is obviously supported, and you'll see as you go through the presentation, the features of the Plus have been expanded to support cable mapping and a lot more advanced analysis on the cable, noise separation, etc. So the Plus device really is becoming the full all-rounder that we intended to be on day one. Moving across the ultrasonic area, we've got three established sensors I'm sure you're familiar with. So the parabolic dish for looking at overhead assets, so insulated stacks on poles, etc. The contact probe for looking in sealed chambers, and then the airborne microphone, just extending the reach of the microphone that's built into the device. So both the bottom two generally aimed at metal-clad switchgear. The new kid on the block, though, and we're going to go into a bit more detail, is the UltraVolt. So this takes the capability of that airborne microphone and puts it inside the switchgear. So where you have a sealed piece of switchgear, we can now get a sensor built into the switchgear itself and give you that repeatability and accuracy. So we'll touch on that in a second. So UltraVolt. So as I say, we launched this probably mid-year, about 6 months ago-ish. We started bringing this to the market. And it's been really well received, to be honest, much better than we anticipated. And I think people like the simplicity of it. Ultrasonic measurement has always been something you do by exception. It's been hard to trend, it's been hard to repeat because of the angle you have to hold the device at, the repeatability, that's always challenging. This changes the story. So as you'll see from the video here, the bolt is mounted in the switchgear. There's a magnetic reader that clips on top, and the reading comes straight up on the device with the ability to hit record. That means that time after time, you're taking the reading in the same place. You can trend it. You're no longer recording by exception. That allows the data analysis to catch developing issues much easier and much earlier on, and also for you to get a better feel for how quickly things are deteriorating, because that consistency is there. It also increases sensitivity because you're inside the switchgear. We haven't got to try and get hold of the signal from a small gap, etc. We are building the sensor into the switchgear. Okay, so just to introduce that a bit further and probably a bit clearer than I've articulated, there's a short video, it's only 30 seconds. I'm just going to press play on this now, and this will give you a bit of an overview to that device.
It looks like a bolt, but it listens for partial discharge. Installed directly into switchgear. Connect your UltraTev Plus 2 to take consistent ultrasonic readings. Faster, simpler, more repeatable surveys, catching partial discharge before it costs you money. It's a simple but powerful device that gets even more from your UltraTev Plus 2. UltraBolt. Order yours today.
Okay, thank you. So you can see for that, really simple in its design, and that's the beauty. It's easy to use. Literally replace a bolt on the switchgear or can be added in addition. The accuracy it gives you and also the repeatability is key. And it really builds on the ethos of the Plus 2, which was a platform that we're going to expand on and keep on adding to keep that consistency of device with yourself and build that wide applicability for you. So that's the latest sensors to be added to the range. The other big change this year is in the data side of things. I'm not going to spend a lot of time on this. We've covered it in previous presentations in detail, but it's worth highlighting that the amount of value we've got and be able to support customers from, and you'll see as you go through the case studies, from the post analysis, not just what you're capturing on site. On site, you're busy, there's lots of distractions, you're trying to make decisions on a small screen. Offline, you can really build the case for the outage, get confidence in what you're doing. And that full user case end-to-end story is what we've seen adopted much more heavily this year. I think we're probably up to, there's about 6,000-7,000 surveys, with each of them with 20 assets or so uploaded. And that's starting to build a really core base which you can reference yourself off. And that's just of this full resolution data as well. So every one of those measurements has got waveforms, it's got phase plots. It's got the stuff that every good device should be recording to allow you to make that informed decision. So one of the big trends we've seen from the year is moving away from amplitude PPC as the end answer. Phase plots, as you'll see as we go through, tell a lot more detail. If you're much more clear of whether you're looking at one issue or two, they also let you observe the type and also the severity and degradation time, the PD. Amplitudes don't necessarily get bigger. So the caution would be is like, look at your processes. If you're only coding those two numbers, it's time to stop and think. There's a lot of evidence to show that coding the wider information now is something that we just absolutely should be doing. I should have mentioned, sorry, at the start, I'll just repeat for now, there is a question function in the corner of the screen, and we will be coming back to questions at the end of the time. We'll make time for that at the end. So if you could raise any questions in the corner on, so we're not ignoring you, the hands raised, but we'll come back to them at the end of the presentation. Thank you. Okay, so data management, key change for the year, really enabling better decisions, allowing us to build the AI functions and help you make better decisions on site, and a step change in the data that you should be recording to get the maximum benefit. Also key if you're going to start looking forward to time to failure and moving towards investment decisions. Okay, so they're the big market trends for ourselves. So we've increased the applicability of the device, and we've concentrated a lot on data support and remote updates, etc., for the device, making it easy to use. We've brought AI features to the device, giving you better access to the information there and then, whether this is PD, whether you should be concerned. And we've built in support through Stuart's and team to help back office analysis for the more tricky cases. So let's look at some of them, what it looks like. So we're going to move on to case studies. I'm going to hand over to Stuart in a second. Stuart's team basically active all year round worldwide, and we're supported by teams in local regions as well, working with yourselves on the ground, either going out and doing full surveys for you, visiting follow-ups when you found PD, or on the other end of the phone to help you with the more challenging cases. So we're going to touch on a few different examples now, and I'm sure you'll find them of interest. So thank you.
Sure. Okay, thank you. So the first one we're going to go through is some cable partial discharge. So we had a project, we were testing about 40 cables, all operating at 35 kV. They all had plug-in type terminations, so we could get easy access using the HFCT onto the cable earth screen at the switchgear end of the cable circuits. The customer wanted to understand the condition of these cables, and we carried out basically HFCT measurements and transient earth voltage measurements on each of the cable circuits. And a couple of the cables showed some evidence of partial discharge, which I'll go through in the next few slides. So the first one is a cable. So you can see from the phase plot, we've got some clustering, 180 degrees apart, opposite polarities, and we can see possible PD. One of the features that we've added this year is around then being able to look at the waveform and be able to actually map the cable from the Ultraset Plus 2 data. So we've got a short little video just showing how we do that, and I'll talk over that as we go through it. So we can, obviously see choose the waveforms. So we captured about 50 waveforms during the recording. And then we can place pointers along the route. So the first one, you place at your initial pulse. So you put that where the first pulse that we pick up, and then we can put another pointer on the end of the cable circuit, and then the final one goes on the location of what we call the location pulse. So that gives us a map of the cable. I'll just go on to a single screen of that. So now we can see from the data that we've got a cable that's approximately 1,000 meters long. We've got an initial pulse that the device picks up. So we've got a HFCT at the end of the cable, and we pick up that initial pulse. And then as the pulses bounce up and down that cable, we can pick up the second pulse, which gives us an indication of where it is. And the time of flight between those two initial pulses provides the location of the partial discharge. So in this case, we're about 66% of the cable route along the circuit. We can then speak to the customer. This particular cable is XLPE, so we've expected joint probably to be in the location that we're picking up the partial discharge from, because partial discharge is quite rare to be in just an XLP cable along the cable route. So then we can compare against the customer's records of the circuit, and we identify that this is in fact a joint location. The maximum recording was around 2,000 picocoulombs, so that is just getting into, so it's amber for a XLPE joints. We say anything over 2,500 is actionable. So the recommendation is to retest in maybe 3 or 6 months time, see if it's increasing. They can prepare for an outage, do some get a jointing kit ready just in case it does fail between that time. But we have historically monitored cables with these kind of levels on for a longer period of time. So in that case, we can compare it, and they can obviously easily go back with their Ultraset Plus 2 and take these measurements, send them to us across the managed survey platform, and we can analyze it and start to trend this level over the coming months. Just as a note as well, on this particular cable circuit, we did take a TEB measurement of the cable termination, and we can see that there's no evidence of partial discharge with that TEB measurement. So because the discharge is 66%, so you're talking 600-700 meters along that cable route, we're not picking up anything with a transient earth voltage sensor on the cable termination. The signal by the time it gets to us is not in the frequency range of the transient earth voltage. So for this particular circuit, we didn't see any PD in that measurement, but only on the HFCT. But then we went to another circuit again with a HFCT measurement. Again, you can see the initial pattern is slightly different, much stronger, and does have these leading edges in there. So it looks a bit more like a possible internal void type problem, and it's much stronger. So again, we carried out the analysis and we had a look at the waveforms. The difference in the waveform is this is much faster. So it's indicating that it could be very local to the cable termination. So I've just got a comparison on the next slide that shows between the two. So we can see in this one that the time between there is around about 1/4 of a microsecond, whereas here we're talking over 1/2 a microsecond. So there's a big difference in the speed of the waveform. You get a lot more ringing in the waveform as well. So again, indicating that this activity is probably much more local to our termination. We're not seeing the reflections that we've seen in our previous one as well, showing an indication of multiple reflections along the cable, indicating a location along the cable route. So then we decided, we thought we'll also take a transient earth voltage, same as we did with the previous one. Again, we've got a really clear partial discharge pattern on the transient earth voltage sensor for this one. So again, because it's local, a lot high frequency, we can see a clear TEV signal. So this clearly differentiates it from the previous measurement and indicates that there's a problem in the cable termination local to the switchgear. The level on this as well is in the red threshold. So in this case, we are recommended that the customer does take an outage and try to narrow down further again, but it's in the cable termination of a particular phase. So much higher frequency, much more distinctive pattern than the previous one. So on this over the testing, we tested 40 cables. Again, using the handheld device, we can locate PD along the cable route and identify between local partial discharge if it's within the switchgear or if it's within the cable. So we separate that activity out in this particular project. I'll hand over to Gareth for the next one.
Brilliant, thank you, Stuart. So I think just to highlight that's cable PD location for the 10-second reading with the CT, clip on CT, around the earth strap, press record on a handheld device, and we're getting all the way to cable mapping with distance to fault. That's not something that's achievable even 18 months, 2 years ago. You turned up to site with a laptop and another piece of kit for any provider. So the device and the software features are being added to the analysis, as you're about to see on this next example as well, are really bringing features that were only available on kind of high-end systems, whether it be per monitoring or otherwise, to this handheld device. So you should be looking, if you're not already, as a service company, to expand the features and the offerings you can do with your device, look to maximise your return. So let's show off another feature and a good case study comes with it. Internal void detection. Noise. So noise is always a challenge for PD, and variable speed drives are particularly troublesome. So in this instance, you can see a phase plot across the base. It's a TEV phase plot. If you're very attuned to it, you can probably see there are two clusters in there just about concentrating within the noise. That isn't easy to see. And certainly on site, I think I'd be guilty of skipping over that occasionally. Going back and looking at the offline analysis, we can use this software tool to separate out the different PD. So if we go on to the next side, you can see here there are two clusters in this top left hand, or three clusters really, this top left hand graph. This is looking at the pulse shape effectively, the energy and the frequency content of that energy in there, the rise times, the widths, and allowing you to see pulses that look different to each other effectively. The top right hand element is looking at sort of 500 samples within that area, allowing you to flick through and see what those waveforms really look like. So they're not the long waveforms we have for location. These are the short waveforms to say whether we think this is a PD pulse or not. By selecting the different groups, you can remove waveforms that look similar and therefore effectively remove the noise. There's the same data with a slightly different view. We're now looking at waveforms that look similar, that look like the RPD, the unipolar reasonable width. And all of a sudden with the noise removed, you've got two very clean clusters. You wouldn't walk past that. And that's the difference that using these analysis tools can make, and really helping you, cut through that noise. The other way of doing this is we could just bin that on site and just not show you the full picture. that's great. And you'll see some systems out there that will just ignore noise, or so we portray. What they are doing as well, though, is throwing the other way pulses at RPD and not giving you that clear shape. This gives you that full control, so you can look below the noise floor, start to see exactly what is going on, what the shape of that PD is, what the classification is likely to be. All that information's there. So the post-analysis approach gives you all the data and allows you to then cut into that detail, rather than making assumptions on the pulse shape up front. And that's really key, and I think supports the right conclusion, gives you the confidence to take the outage. So challenging set of noise. 18 months ago, again, that would have been really hard to separate on site, or separate at all. Now the device is collecting that information. It's the same device many might have bought 4 or 5 years ago. It's just a free software upgrade, and we are then collecting all that information to be able to drive these high-end features for you. So please upgrade if you haven't done to the latest version 5 software, and give this a go. To yourself again, Stuart.
Okay. So now I've just got 3 or 4 examples of ultrasonics, and ultrasonics is very common. We do see it around the place, virtually a lot of surveys, we see quite a lot of ultrasonic activity. So just put some classic examples that we found this year on different types and different areas of switchgear types and things like that. So the first one is a air insulated switchgear. Again, we picked up our clear PD. So this is just using a flexible microphone around the edges of the cable termination box on this particular panel, and we can hear the PD. So I'll play that for you. This particular survey had been done just before an outage, so we made the recording, we spoke to the customer, and we advised them that there's a possible problem in this panel, so that you could open it up and they had a look, and we can see the clear tracking across the surface of that area there. I don't think it would have lasted too much longer. A lot of these things are affected by humidity as well, so try and control the humidity in your substations. Sorry. Right, back through to the next one, sorry. The next one that we've got is a classic main intake substation at a site. This site, we'd never tested it before. It's the first time we've been to site, and it's an air insulated VMX switchboard. So we've seen this very common. We've done some big projects on that type of switchgear historically, and we picked up 4 different partial discharge sources on there. So we're still finding examples of this. It's generally down to the environment. So if you've got air insulated vertical racking type equipment, then you want to try and keep the humidity in the substations as low as you can, particularly below about 40% if you can. And this one we've got 4 different circuit breakers all discharging away. And again, I've got an example of the sound file that we recorded from that one, from one of those. You can hear it.
Well, it's worth saying at this point, Stuart. So ultrasonic readings, you said before, probably about 70% of what we find PD-wise ultrasonic based. Those sound files are those to the trained ear, very clearly RPD, they've got the randomness in there, etc. Aren't that easy to distinguish on site, and certainly it's really hard to train people in that manner. So you'll find the device has got a built-in classifier. It's very accurate for the airborne approaches, and that will classify whether it's PD or not. So you haven't got to go to that level of training. And again, I think it's a key element of the device you should be looking for.
Yep. And we can see the clear phase plot as well recorded on this. So we can see two areas raised, 2 groups of activity, 180 degrees apart, indicating clear surface partial discharge characteristics. This picture in the top corner is a stock picture, but it's the same type of switchgear, and probably a problem they'll find when they open up that board. Okay, another one is cable termination boxes. So this one is a RMU cable termination box, and my colleague has nicely used his pen to point exactly where he's took the measurement from, but it's right in that corner. We've got a little tiny air gap in the corner there that we're picking up this sound file through. So that was the historically that's how you've got to take these measurements, and we have managed to pick it up, and we can have a listen to it now. As you can see, it's quite quiet, and you've got to make sure you've got your microphone in exactly the right area. So it does take a bit of people making sure they're listening right round all those gaps in the cable termination boxes. Obviously, if we can install the Ultra Bolt into these cable termination boxes, then that would eliminate that chance of missing something. I imagine if we open this up, it'll be considerably louder inside, and obviously the Ultra Bolt will be much stronger signal, but we're picking up through this tiny little hole in the top right, basically the fold of the steel in the top right hand corner there. So it's that would be a big improvement to use the Ultra Bolts on these ones. And then finally is a parabolic dish one on a pole termination. Again, we can do this from ground level using the parabolic dish. We're listening from the ground and pointing around the cable termination. There's probably 2 phases involved. Can we see the first cluster and then start the second one there? And we can have a listen to this. Again, easy to identify from a ground level using we're using the microphone. Okay, next one is back to another internal void one for you.
It is. So another internal void example, and again, this is another high noise example. So unfortunately, more and more of the sites we go to have got high noise. Quite often setups like this, and this is actually a case study you can see from the sunny skies. We should be thanking our colleagues in Australia for. Unfortunately, didn't quite get that weather here, but they've got basically 3 inverters right next to a ring main unit there. So from an electrical noise point of view, this is quite high and relatively challenging to look for PD in, especially where everything's energized. So 3-panel RMU, we're testing with TEV on this, and actually on the cables, I believe. I think was on the outside the cables, the easiest place to get access to. So this is the data that's come through. You can certainly see there is a cloud of data there. So without doing any further analysis, you can see that we've got a band of noise right across. We've got some activity, kind of 180 degrees to sort of 260 sort of level. Maybe if you really squint, you can see something in the sort of 0 to 60 sort of area. On top of that, there's some other weirdness going on, kind of at the 100-degree mark, and generally it's a real mix of signals. Again, picking up the TF mapping and looking at, it's not pure TF mapping, there's some extra bits on it, but effectively TF mapping, we can then separate the data between the 2. You'll see there one group and one cluster is very much looking at the background noise, and that pulls out all the electronic noise that we're seeing, which was interfering with our signal. And the left-hand plot now shows the 2 clear PD clusters. So really gives you confidence to take that next step, to take maybe the outage, or in this case, as it was to let's remove the electrical noise and prove that that source is actually there. So you can see the 2 half clusters there. This is the same measurement, but with inverters on both sides of the string and also locally there turned off, and we can see the background noise now goes, and we've just got the pure PD signal. So it's a raw data capture, but with that background noise removed. So you've been able to go from really struggling to see a signal within the noise to be able to see below the noise floor and pulling out everything we think is associated with PD, give you some confidence to take the switching to then see that, okay, actually, we can therefore get this really clear output with the noise removed, and then go on to investigate and locate. So just giving you that confidence, just removing the noise and just making the whole picture clearer for you. So this is not done live on the device. You capture live on the device, test record, 10-second recording. It's then the features there built into the SD card files, basically the HTML viewer on the device, and you can view and analyze your data as you wish. So again, that's there. It's freely available to all of you to download. So that brings us to the end of kind of the case studies on the UltraServe Plus 2. We're going to touch now on some offline case studies, or the one in particular, really. Offline testing still has a place. So we've talked very much about how much the handheld devices have moved on. When we talk about offline testing now, this isn't our kit. We're using a third-party kit to support our customers. There are some cables and some switch you can't get access to the terminations. There's other bits where you found PD and you want to confirm the location before you dig, etc., or overlay. And this is where the offline cable testing comes in. This technology has really moved on as well over the last few years. You'll see the size of the kit has reduced. It's much more portable. We no longer turn up with full test vans to do this. But it still requires specialist knowledge to get the right answers out of it. And that's where Stuart and his team come in. So with that, I'll hand you over to Stuart.
Okay. Yep. So as Gareth mentioned, this is a service offering that EA Technology provide. EA Technology have been doing partial discharge cable mapping as a company since mid-1990s. We had big test vans with 5 Arista stacks lined up in the back of it to create a very low frequency power supply. But obviously since then there's been a lot more improvement in the market. So we now use third party equipment to test these cables. But obviously the knowledge is still within EA Technology. So although this is getting better and better, and the software it does get better all the time, it still does take a lot of much more knowledge to understand the analysis of this data. So just before we step through an example of an offline cable testing project, again, it's very much important to reference, to understand the location of every PD source that we find, and that's what we're show the importance of that, and then comparing against the records and making sure the records are correct. Because in the UK, a lot of circuits are mixed materials. So this particular one that we're going to talk about today has mostly paper insulated cable. So paper insulated cable historically would have partial discharge. There's little voids all the way along it when you've got wraps of cable going around, and if they've got wax and stuff in there, it'll generally be okay for long periods of time. But then XLPE, over the years, there's been a failure in the cable or something like that, so areas of the cable get replaced with new modern XLPE cable, which isn't very tolerant to partial discharge at all. If you get PD in that section, then it's going to fail in quite a short period of time. So when we're doing these offline tests or the online ones, if we've got the access, then we do need to ensure that we're locating every partial discharge and ensuring that it's in either the XLP section or a paper insulated section of the cable. So I'll just explain a little bit what we do. So we're going to energize the cable. The difference with offline testing as well is you can raise the voltage slowly. So you're not going to go from 0 to full voltage, and you have the advantage of also going above operating voltage. So you can do things like tan delta at the same time, and you can stress the cable a little bit more and pick up any PD or up to generally 1.5 times operating voltage these days. And we can do this over. It's about an hour to an hour and a half worth of testing for a cable circuit, and we focus on PD and tan delta. So we capture hundreds of waveforms during the survey, and some of them will be noise, and we see fast frequency so we can discard those, and then we want to look for the PD waveforms. So these PD type ones, similar to what we were looking at before, fast unipolar pulses, and we can look at the reflections and locate exactly the same technology as what we're doing on the UltraServe Plus 2. So the technique for doing it is you mark your initial pulse, location pulse, and the end one. With this, generally you get more locations because you've got varying voltages, so you can pick up some at lower voltage and then some might come in at a higher voltage. So we can plot all those along the cable, and at the end of the testing you will end up with a map of the cable circuit that we can then do the activity on. So following the analysis of the data, we put in locations of the joints that have been provided by the customer, and we could produce a map of that cable. But the worrying thing was it did indicate some partial discharge within XLP sections of the cable. So I'll just show you that. So these two lines here are the joints that were provided originally, and obviously all these dots are areas of partial discharge. So we went back to the customer and recommended they recheck where their cable terminations or where their joints are in the cable. So the customer then was concerned, so they walked along the cable route and put in the new switch and measured where all the cable joints were. That's the indicator they're in a slightly different position to where they were originally. And we could then place them back on the map against the data that we'd recorded. So then that actually indicated that the PD was in this area, meaning that the actual XLP section was this area, not the original area originally. So the customer was much more rewarded that there wasn't any partial discharge now in that area of the cable circuit. But it does just show how location of the partial discharge and obviously against customer records is important when we're doing these cable circuits. And this last little picture is just one that I've added that we were doing a cable testing job and we energized the cable. We got up to half the operating voltage, and the tan delta measurement literally went off the scale. So we stopped the test at that point and opened up the end of and opened up the terminations of the cable and found this quite advanced partial discharge, but the cable was out of service when we got to site, so we couldn't do a handheld partial discharge survey. So sometimes cable testing can also find problems in your cable terminations as well.
Obviously, I would have shelled up and handheld.
Yeah, it was short with ultrasonics.
Clear one there.
Chance, yeah.
Brilliant. Thank you, Stuart. And obviously, so I think it's worth highlighting we're available to support if you do find stuff with your handheld device, both let's say back office looking data for you, but also coming to site to follow up services such as this to give you that confidence to take the outage. And that's really where this comes in, plus where you haven't got access to your cable sheaths. Okay, I've seen lots of questions come in. Before we move on to them, just got a couple of slides to touch on. So firstly, a big thank you. It's really enjoyable looking through LinkedIn through the year and seeing all of you using our devices and the good case studies you're coming up with. It's also a really good education piece for everybody in terms of what's what people are finding, what's common in the field, what's changing, because switchgear does new versions come out, more common things come up. So I think that if you can keep sharing that, there's a QR code there. Please do. Please ask us questions on there. We're more than happy to come back and respond to case studies, etc. And just support you to get the most out of the devices. So yeah, please keep sharing. Please support each other. Okay. Also to note, just from a sales point of view, there is a current offer on. So we mentioned on your Ultra Bolts. These are selling really well at the moment, but there's still an offer running until Christmas. So please, get in touch if you are interested in getting hold of the new bolts and adding them to your +2, and that offer's running. There's also, if you enjoyed the conversation today, there's a training element of our business, EA training, and we've launched this online course this year, so it's globally accessible. Basically giving you electrical distribution background and competence in that area. So it's a fully online course. You can enroll digitally, and yeah, please take a look. It'll give you just a wide background and knowledge really to that area. So that's the other thing to note. Okay, another question. So I can see the announcement. Slide 34, the split between the noise and PD and the TF map seem very arbitrary. How does software make this split, or is it manual? So currently the split is manual, and it is slightly arbitrary. You can see the identity of the two plots. The software tool as you use it will see is very intuitive. You literally circle areas and you can see what that pulls out of the phase plot. You can also drive that backwards. So you can pick a small area you know is PD. So say you see one cluster only or a part of the high amplitude clusters. That will highlight the right part of the TF map for you. And then you can look at associated points around there. So it's a slightly iterative process. I dare say it will become more automated as time goes on, but the software tool is very intuitive and allows you to do that two-way approach. So you should find that fairly straightforward to pull out that extra information. So I hope that answers that question. I was commenting here, I think, of questions. So what type of PD method for bolt inspection? So what PD type, sorry, for method of bolt inspection? So the bolt is purely looking at ultrasonics. It's an ultrasonic based microphone. We use ultrasonic for surface activity. So surface PD, obviously if it's an internal void, the audio output from it, the sound won't escape from the void easily. So it's just surface with an air path required. So it's basically taking opportunities where you would have used previously the contact probe, or whether you would have used the air probe as an accessory or the built-in sensor on the plus through a small gap, and adding that consistency and increased sensitivity for you. Okay, next question, I think, seems to be how to save the site records on an UltraTev2 device. Okay, I'll give you a long answer to this and a short answer. The short answer is press the red button in the middle of the screen. So you'll see front and center of the screen, the middle button on every measurement page is record. When you press that, it will guide you through a 10-second recording. It'll start capturing for 10 seconds and then ask you for basic asset information. So the asset information is there, so you've got some structure to the data and you can replay that when you're back off site. That record function will initially store the data into the SD card on the device as a zip file. And that zip file contains a HTML. So you literally unzip the device, open the HTML, and you can view the data. And that's where you'll find the TF mapping, etc. The other option is you can connect to our cloud service. And you'll see in the bottom right-hand corner of your screen on the homepage of the device a cloud function. You can connect to that and you can upload the data to the cloud over Wi-Fi and do all the analysis you just shown in terms of location on the time of flight, etc. for KLPD, seeing historic readings from the cloud. If you're using a cloud connection, it has the advantage that you can actually plan your surveys. So you can have all your asset information stored centrally. You can go as far as being very prescriptive what to collect on site and guide repeat surveys. So we've covered that in other webinars, but more than happy to have one-to-one calls if anyone wants to know more about recording features or how we can help manage the data. I think we've got time for a couple more questions. So next one, 2 seconds. What's the maximum testing voltage rating on this device? Okay, all of our measurements are secondary measurements, so we are not connecting to the HV supply. So the absolute maximum voltage isn't governed by that. What changes as you go up the voltages tends to be what techniques you use for detection of PD and what level you're actually interested in it being a concern. So the device will cover everything from kind of low levels where PD starts to become an issue, maybe 1 to 3 sort of kV. Right through to 500 kV switchgear assets. At the lower end, you tend to be using the TEV, the ultrasonics, and maybe the HFCT. At the higher end, you'll tend to be using the UHF techniques and the HFCT and still TEV, but they seem to be more common. So you're bringing the UHF in. But it will cover the full range just with different sensors. And that, I think, so one last question there I think we might have missed. In the case study 2, you have a TF map. I've seen other competitors using this approach. Is a TF map a standardized process, just a double internal way of analyzing PD patterns? So TF mapping, you'll find, comes a lot from the motor background. If anyone does a lot of motor testing, you'll see that's in the standards and described within there. So it's a well-established process. You will find it used on higher end devices. When I say higher end, I mean lab type devices and also permanent monitoring devices. I'm not aware of any other handheld device that gives you this information and the ability to be able to separate noise into this level without throwing away the detail. We are capturing waveforms for the full 10 seconds, with allowing you to then post-analyze that in some considerable detail to really give you the confidence on that PD. I don't believe any other, I stand corrected, I don't believe any other device for handhelds does that on the market at the moment. Oh, another second to any other questions, but I think, apologies if we've missed any of the questions in the chat. I think we've covered them all. If there are any, we will come back to you directly following the webinar in writing and get a response to you. If not, okay, there's one more from...
Which is the dangerous PD?
Which is the dangerous? Yeah, okay, we'll answer this one. Which one's the dangerous, internal or external PD? So no PD is ideal. I would probably say internal PD tends to progress slower, and you tend to have the surface activity, once you've found that, it will progress reasonably quickly, especially if things like high humidity are present. So in terms of time to failure, you're probably going to get more warning off an internal source than you are off an external, but it's a very general comment. I think in terms of what you can do more about, quite often it's the opposite way around. So if you find a external or surface activity, things like controlling the environment, separating cores, moving the stress away, there's quite often really simple interventions you can do for surface, or as you call it, external activity, which are cheap and easy to do and will make a big difference to the lifespan of the gear. That is harder on the internal side. The internal, you're heading towards component replacement. Okay, so I'm going to call it there. So we'll follow up any questions that are still coming through. Thank you for your questions. It's really good to see. And I think from our side, all that's left is to thank you for your time this year. It's been great to work with you, and really look forward to working with you going forward in 26 and continuing to improve and develop the instruments and the success you guys have. Thank you very much for your time.
Yeah, thank you. See you in 2026.
Indeed.